Okay, so I just wanted to tell kind of somewhat broadly and somewhat more specifically about what I have been doing in my research. So this talk will have like two zooms, right? One on the like big picture and one on the grasshopper. And the big picture is the math game. So the thing is that we like back in 2017 there was this huge thing that suddenly like computers can play like the very hard game of Go and superhuman performance, and back then like people were like, oh yeah, let's do the same for math and we can solve like all of math, but somehow it's much harder. And I've seen many bad excuses why it's harder, right? Like people are saying like, oh yeah, it's harder because the space state is infinite and not like large, but like once when the space state is like 19 squared factorial or whatever, then like it doesn't really matter whether it's not infinite or not. I mean, when I'm referring to Go. Also, like another excuse that it's undecidable. So you cannot compare it with the standard like computer computational complexity hierarchy, right? But also the computational complexity hierarchy also doesn't feel like too relevant in just when what people are doing when they get a problem and then start thinking about it, because the problems are kind of specific. So I think that the real problem is that we don't really know what the game is, right? Like, and the thing is that we developed logic, and like logic was developed back like, I don't know, 100 years ago, but recently like there were like computer systems developing, first Mizar and then Isabel and so on, and Lean is quite trendy nowadays, and these systems are became quite good at representing proofs, but it still doesn't always feel like solving the problems. And so I wanted to like understand more on concrete examples what would feel more like solving problems. And I get that in general math there is also kind of the objection that what mathematicians are doing is sometimes a bit fuzzy, and sometimes my games were also a bit fuzzy. But so the point is that maybe there is some like partial way to formalize what we are doing and have it kind of more rigid than, for example, now there is the popular approach of doing everything with LLMs, and you give it to LLM and LLM has no idea what it is doing. So like have it more formal than that, but still maybe there should be something less formal than the strict logic of whatever Lean or something like that. And so I was looking at various games, and these are the games that I was looking for. Euclidean geometry, and then two games, Sokoban and Hex. I will tell a bit more about them now. So Euclidean geometry. Euclidean geometry is a topic of IMO. It's like 1/4 of IMO, so it's a great kind of subject to look at math. And I developed a system for that. It looks basically like this window, and show a demo if there is time, but maybe at the end I could show some demos of the other systems, but now I just want to show that like I made this thing which looked kind of like GeoGebra, but also understood the logical inference steps. And there were some aspects of the logic. So when I try to like look more from the distance and just like state very basic in very basic terms what are the main aspects of the logic, these are these. So first, it's object-oriented reasoning. It's kind of a funny reference to object-oriented programming, right? But what I really mean is that at certain problems, and in particular in geometry, but also, for example, in combinatorics, the focus is not on the statements, but on the objects that we are dealing with. Right? Like what the user wants to see are the circles and not a list of all the statements that we know about the picture. So one thing is like how to display it, and also how to make steps, right? So the main step that you can do is to like actually click on some of the objects and say, hey, I want to construct a new line, or maybe I want to do this inference step, and the inference step has some objects as inputs, the parameters, right? How much of the universe. Then it has some assumptions, and the assumptions are checked in the background if they have been proven or not. If they have not been proven, you cannot do the step, right? That the system tells you that you cannot do that. But the point is that it's kind of a shift of focus from what we see in standard IPPs. Second, quite crucial feature of the system, for example, alpha geometry has the same feature, and it's a question if it's a feature or a bug, honestly. And this is semi-formal logic, because when I'm proving something in this environment, or when alpha geometry is proving something, it's actually not proving a mathematical statement that you could just say, okay, now I have fully formalized the IMO problem. It's only proving it in a particular diagram, and it's checking some of the topological facts using that diagram. So I think it can help with like focusing what's actually the core of the problem, but when we want to then get from such a proof to a proper proof, it's a pain again, right? So that's a question if how crucial this is. But alpha geometry uses it, the geometry uses it. And then of course, like it's easier to solve it inside such a system than with a system that can do like fuller reasoning. And third step is that I just needed kind of good enough automation for doing the background checks, right? Like when I want to apply a theorem, I want to check that the assumptions are satisfied, and the assumptions like there is in particular in geometry, like the automation is mostly driven forward, so it just like it deduces all the facts that it can trivially deduce, and then it stores them in database. But also for angle chasing, like this is like very easily decidable. It's kind of some sort of Gaussian elimination, so we just implement it. And you do not need to annoy the user much with like some logical form, not logical, but algebraic manipulation. So that's something that I've done, I don't know, maybe 5 years ago or something like that. And then I was, okay, so I want to do like not only geometry, I also want to do combinatorics. I always enjoyed combinatorics, but combinatorics is hard. So I've decided to just look at puzzle games, because I also like puzzles. So Sokoban, in case you don't know what it is a game where you are kind of a character that can move. So this blue dot is the character, and it can move to other blue dots. It just like automatically shows you everywhere it can move. And then there are boxes, and it can push boxes, and it can always push only one box at a time, and it can only push, it cannot move or anything like that. And it must get all the boxes due to the storages up there. And now you can say, well, like, but there are only 2 boxes, and there are like too many storages, and the reason is that it's an abstracted state. I will explain. What I want to say, yeah. So first, like what I'm actually like proving with Sokoman, right? Sokoman is a game. It's not a math problem, but what you can how you can turn it into a problem that you want to prove is that you take a position in Sokoman that is not solvable, and you want to prove that it is not solvable. So then it's like perfectly rigid reasoning task to prove that you cannot solve a particular position, for example, this one. And if you want to prove that something is unsolvable, then the most direct way of doing it is to go through all the options. So what you are showing to the user is kind of close to just showing the standard game and doing like this state space search. But the difference is that like there are too many states, so what you want to do is state abstraction. And that's what happened in this picture. That you originally want to prove that like the position with all the boxes, the two orange boxes and all the gray boxes is unsolvable. And the user, when he wants to prove it, he says, well, like the gray boxes are irrelevant, so he somehow clicks on them and says, hey, like these boxes I don't need, and now I will do only the space search on the orange boxes, which will be much shorter, and it will arrive to a proof reasonably quick. And so that's the basic idea of how I can prove unsolvability. And the other kind of crucial feature of this is that whenever the user actually proves that something is unsolvable, this fact is stored in a global database of the positions that are unsolvable, and the computer knows that like whenever that there is no point in reaching such space. So there is some automation which is inside this database. And kind of similar is Hex. So Hex is a game where it's actually a two-player game. One player is blue and one player is red, and the goal of the red player, like this is not showing the full game, this is just showing some kind of partial problem in the game. And the problem is that the red player wants to connect to this bottom line, and the blue player can block it, and like the players alternate in their moves. And again, similar like a Sokoban, the user environment looks like the space state search. There is some. I think I will not go into the detail of the second point because it always just confuses people. But kind of the idea is that if you want to know what are the even reasonable moves of the opponent to search, the first thing you do is to show how you would solve the problem if the opponent didn't play at all. And then the opponent knows that he must play into the region when you did it. And in Hex, there is automatic backtracking generalization in the program, which means that if you, and that's kind of like important exactly for like doing things like understanding what is the minimal set of hexes that you needed to connect to a site. And together with this, there is again the global database of proven facts that can be used automatically. And this feature like both in Hex and Sokoban, this like backtracking, it's always like doing case splits, and then it does it has this global database. So this is something that I usually call it CDC-like style. If you've heard of this feature in SAT solvers. So I don't have a slide for it, but in SAT solvers the main feature of how such solvers are this successful, like such solvers are some programs that can solve NP-complete problems reasonably efficiently. And they do basically this, they do like huge case split, and then when they backtrack, they do some automation and then store it into a global database, what they have proven. So that's the main idea. And it turns out to be quite useful even in practical problems that are not necessarily like NP-complete, like both Hex and Sokoban are p-space complete. So these are the games that I looked at before. And now let me look at the grasshopper. So do I? Yes. So grasshopper is an actual combinatorics and problem. Of course, the disadvantage is that it is just a single problem, right? Like I cannot go too far, and I cannot make an environment for all of combinatorics. But I thought, okay, let's move from toy problems to some problem that actually appeared in IMO, and it's quite hard. And so what I will do now is explain what the problem is about, how a solution looks like, and then show some attempt to make an environment for it. So what the problem is about. We have a grasshopper, and the grasshopper is thinking about some jumps that it wants to do. It wants to jump by 1, it wants to jump by 3, it wants to jump by 4. It's a finite set of distinct integers, positive, and then it's standing in front of a minefield. And the length of the minefield is chosen so that if the grasshopper uses each of these jumps exactly once, it will get exactly to the end of the minefield. Right? So it jumps 1 and then 3 and then 4. It will be at the end, but it explodes in the meantime if it chooses this permutation. So the only task is to prove that it is possible to choose some others, like any permutation that actually avoids all the mines that are in the minefield. Kind of obviously, it's important that there are less mines than it has jumps, because if I could pick like 3 mines to put there, I could block each of the possible first jump of the grasshopper, and then the grasshopper will be screwed. But when there are less mines than the jumps, the grasshopper can do it. And so what I will now do is to present a proof of how this problem can be proven. And so the idea is that first idea is induction. So let's say that the grasshopper can jump with some big jump, let's say even the biggest jump to an empty square. And then like, if it jumps over a mine, then we just use induction on the rest. So this is the ideal case, this is the dream. And it doesn't always work that easily because of 2 issues. One issue is that the first jump that it takes could land on a mine, so it cannot do it like that. And then we could say, well, then it could use the second biggest, but then like that could also land on a mine. So maybe we want to choose a small jump, but then there's the other problem, and the other problem is that if all mines are far away, then we cannot afford ourselves to use the induction hypothesis, because the induction hypothesis is assuming that there are strictly less mines than jumps, and we use already 1 mine, so we also need to use we used 1 jump, we need to use 1 mine. So how to resolve these problems? So let's focus on the case when all the mines are far away. And there is kind of just manipulation tricks of what we do with these lists. So we find the first mine that's there and we imagine as if it was not there. And we imagine then we can happily apply induction. And if the induction doesn't hit this mine, we are happy. So we kind of assume that the induction will hit the mine that we imagine is not there. And what then, the only thing that we need to do is to fix the order of the jumps. And it actually can be done because if we look at the jump that is jumping outside of the mine, it's shorter than the biggest jump that we took at the beginning. So we can just insert this biggest jump to jump over that white mine, and then like what happens at the beginning doesn't matter because there are no mines. So that's the case when everything is far away. We solved it with this little trick. What if we land on a mine? Well, we can try the same, right? Like that's what we are used to. We find a method to solve something, so we do the same. We say we ignore that there was a mine, who cares, and we apply induction, and then we swap the two chunks. The difficulty is that now we are not really sure if there were no mines before, right? So it's not as clear that we can do this. So we need to somehow ensure that the induction that we run here will not give us the first mine that will land here. But there is still a trick to resolve this, because when there are two mines at the beginning, it means that we can allow to insert a new mine into that list after this one. So the solution that actually works is the one that looks at all the mines that were before and imagines them moved exactly by this biggest jump. And if we do this, then we can run the induction hypothesis, because the mine that we removed is this one. So we still removed at least one mine, and we are allowed to run the induction hypothesis. And then when we swap the two jumps, you know that we do not land on the mine before, because that's how we prepare it. Okay. Problem solved, right? Very nice. And then I was implementing an environment to basically be able to replay this solution to an extent. It's not perfect, and I will show it, but like I will. But first, I wanted to like say the basic ideas that were appearing there that I try to follow. I again try to follow the object-oriented reasoning. I want the user to see the objects and not the facts. Maybe it's a bit annoying actually in this case, because you will probably want to see more facts than I will be displaying. But I still think that from the controls perspective, it's kind of closer to how mathematicians are like playing this problem. Kind of an important feature that it has is the automatic case split when you try to do construction that has assumptions. So if you apply, let's say, a theorem, let's say in ITP like clean, and the theorem has some assumptions, then what happens is that suddenly you need to prove these assumptions, and that doesn't have to be possible. But what we often actually want in these combinatorics like programs is that you want to say, well, okay, so I will prove it now under this assumption, and then I will prove it later in the case when the assumption is false. And third, like the last point is basically again related to the object-oriented reasoning, that I need to have a way to display these objects, and that means that I always create some model, ask some like SMT solver to give me some examples of how the things could look like, what the lengths of things would be. So this is about the idea. So let me try to show you it in practice. So we have this case. We have a list of mines, a list of jumps. So we have like, we imagine that it could be 4 and it could be of this length, and we have like a list of mines that there could be 3 mines. And so the first step that we do is to take the maximum jump out of this multi-set. It's purple. The purple means that it's not multi-set. And let's say that this is how the maximum jump is. This is the size of the maximum jump. Then what we do is that we cut the mines here. And when I cut it, it immediately like jumps into a subcase, because it's not always possible to cut the mines after the biggest jump, in case the biggest jump is everything we have. Because the mine field is kind of a list of booleans would be one size shorter than when I want to cut it.
How can 3 different jumps go over distance 3?
That's a good question. The thing is that that it doesn't look like into the model fully, right? It's just like it has only some of the axioms that could be true. So it knows that what does it know? Like it should know some inequality, but I agree that it's quite weird that there could be 3 jumps of length 1, 2, yeah, of length 3, right? So it knows that the length is at least the number of jumps, but it kind of doesn't come with the idea that the jumps must be different and therefore the length must be bigger, which is a bit harder to implement because I'm running just a linear logic and this is quadratic. So, but I can change the model if this is like disturbing, and I can make this bigger.
Oh, well, it would have to be 6.
6? Okay.
And now the biggest jump is not the biggest.
Come on. No problems. Is it enough? 1, 2, 3, right? And it's 7. Happy. Okay. So now what we do is to apply the induction hypothesis on the rest of the jumps and the rest of the mines. And what happened is, one is that it turned black, which means that now it's ordered and not unordered. When it was purple, it was unordered. And second, what happened is that it said, well, now I'm entering again some subcase, which is saying that the number here is the number of jumps here is strictly bigger than the number of mines here. And so now what I could do, I could say, well, I think this would be the solution. So let's try, say this is the solution. And it tells me, well, like in case there is no mine at this spot, which is this case, I'm happy. Now show me what to do when there is a mine. So to do something, I think now it's a bit more tricky. So one is that I actually want to isolate this mine, and second, I want to revert this order because this order was stupid. I want to use the induction hypothesis different way now, right? And so now what I do is that if you remember the solution, like unfortunately I cannot motivate the solution as well as in the talk, and that's why I'm showing the environment after I show the solution, because this is a step that requires a bit understanding of what I want to do. So now what I want to do is I want to like union this beginning from these with these jumps. And because they are of different size, I first want to cut them to make them the same size, which again enters some subcase. Then I say I union them, and then I do the induction over this. And I move all the lines back, and now I wrote what is the first jump here, and it tells me, well, the first jump is of size 1, and it already kind of knows that when the jump is 1, there could be no mine here, and therefore it's also no mine here. So that means that I can swap these two jumps and say this is the solution. And now it tells me, okay, now you have to go back and tell me what to do. And when we were unioning these two things, you assumed that the bottom one was longer. So I need to basically do the same idea. This is the upper one longer. Induction. Reset. Take the first jump, swap it with the maximum one, and say this is the solution. And now we enter the case part away. Now it tells us, well, like you couldn't apply the induction hypothesis because all the mines are actually down here. So what we need to do is to first find which mine was the first one, and let's say it was here, and then actually replace this mine. So far, like, nothing happened, but only like I found the first mine, and now I can replace it with an empty list, and say I will call the induction hypothesis on the same thing where I replace the first line with this empty induction. And wait, so now what was the trick? Now we wanted to know what was the jump that was jumping over this. And like that's basically, we need to know what is the jump that is jumping over this division. So how did I do it?
You swap jumps.
Huh?
You swap like the
Yeah, that's true. That's true. Yes. Okay. So just to explain what happened now, because this was probably kind of a fast step. So let me just make this bigger again. So there were these, like, I had this list of jumps, and now I found the single jump that jumps over this edge, because this will be the jump that I want to replace with the biggest one. And so let me do it. Let's just move it here, right? And say this is the solution. And it's happy. And now it tells me, like, you couldn't cut the mines because there's nothing here. But that's easy because this is already the solution, because there are no mines. So I say this is the solution. It's happy, right? So this is like how I imagine in an environment that's at least able to follow reasonably closely what I showed in the presentation. And of course, it's still like not perfect, and there are many challenges. So one challenge is the automation that I need to actually do the things in background that are reasonably obvious requires like linear integer arithmetics, but that's not such a big deal. I can just call an SMT solver. But it also requires to do correct instantiations, which is not as simple. And I do the instantiations in kind of a handcrafted way, because when I try to just run SMT solver on the higher level problems that I let it to do the instantiations, it doesn't solve all the problems that I would like it to be able to solve. And of course, it works on the demo that I showed, but then we would want it to work also in other examples when other people would be playing with it. and it's not that robust at all at this point. So maybe like a good solution would be rather to provide the user some tools to help it prove things and know where to instantiate. Another challenge is how the backtracking should work, right? So in the games, I had this CDCL like style, and that's not something that would be happening in the grasshopper currently, because it feels like when you know the solution, you do not need it as much in such mathematical problems. But I think that it still could be quite useful when you do not know the solution. You're just playing with it, because then it means that you do not need to reprove things, that you like said, okay, I try to prove this, and then you undo, and then you do it again. And another kind of a hack that was there in the environment was the one when I said, okay, like I do induction, and then I actually don't like the induction that I have done in this case, right? Like I got somewhere below, it did a case split, and then what I want is to say, well, I have done some step, but this step should be kind of independent with the search tree in the cases. And currently there is a hack that I can just say, well, like return this and make it purple again, like undo the construction. But I think there should be a more robust way of figuring out like how exactly to make such independent like backtracking. And another challenge is that the environment is not able to like do all the motivation that I was showing in the slides, and one of the reason is that some of the motivation was kind of more higher order, especially the one that motivates you to take the lines before and shift them. And also like another higher order trick that feels very natural for a human, that human doesn't even think about it, but it feels like cheating when like I implement the environment that is a bit overfitted again, is that there are two ways to state the problem. The original problem was stated that there are n-1 lines, right? And there is exactly one less line than we have jumps. But what we are in the end actually proving with the induction, and it's much more convenient, is to say there are strictly less lines than jumps. Because like the kind of annoyance is that when we are doing, for example, this shifting, there could be some lines over here, right? And then we could merge them. So that's something that like people do not even care about too much, but it's something that I don't know how to formalize well, and maybe it's something that's actually the part that's not really like that is informal in the problem solving part of the problem, and yeah, that's all I wanted to say. Maybe I have more time, so. But I could answer questions, I could show other environments. So thank you for the attention, and I'm happy to serve it for the rest.
Yeah, maybe we can take questions from this room and from the online participants, and if there's time left after that, we can maybe move to another demo. So has anyone got any questions here?
I guess for geometry, you probably do rely on visual intuition, but I guess the other question, do you tend to rely a lot on visual intuition for your combinatoric solutions, or do you tend to approach it more from an abstract point of view?
Well, you mean as in when I solve combinatorial?
Yeah, I guess what you solved prior to formalizing.
like, I think when I'm solving the problem as a human problem solver, I'm like drawing pictures all the time. So I think I rely quite a lot on visual intuition. And of course, like there are some like fake proofs, right? Like the two favorite fake proofs that I know that exploit this, that people like rely on visual intuition. One is geometry and one is combinatory, right? And I can show you fake proof of four-color theorem, you know. It's quite convincing. And I think like people actually like originally thought this was a real solution, right? And that's eventually realized that it was, you know. And yes, so yeah, I think that usually that is kind of the thing, right? That combinatories and geometry are more, people use more visual intuition in solving than some sort of more algebraic problem. But like I like, right? But like these are the IMO style problems, right? So then I don't know actually. Math is broad, right? So I think everyone has to answer for himself how much you use visual intuitions in different kinds of problems. I feel like in set theory I also often have some visual intuition.
So there's some sort of slightly difference in nature between the first example you showed of like Euclidean geometry and like the second half, which is like there's a lot of problems you can pose in Euclidean geometry and just kind of you design one space and then you can play with a lot of different problems. But here you kind of have to design one kind of playground for one particular problem. So kind of the question is
How to
how to like that's the, I think that's kind of the whole question maybe is like how can you make this playground in a way that's kind of flexible enough that like you don't need to rebuild the playground from scratch each time you have a slightly different
Yeah, I agree. I think that's the challenging question, of course. That and like I cannot guarantee that it is possible to generalize, right? But the reason why geometry could be so general is that it is very monolithic from the beginning. So like then like I would say that the geometry is about as monolithic as like a hex is monolithic. Even right, like maybe slightly less, but like it's really so yes. I'm sorry, I don't have a good answer, right? Like how to generalize these things, but I would like to, right? That's so I think that the reason why I'm looking at the particular examples is because I think I can even on the particular examples observe some general principles that would apply more generally, such as this object-oriented reasoning, for example, and automatic case splits, right? That's something very general.
Are there any other questions? How about online?
This one here.
Yeah, there is one.
Oh, I'm sorry.
What was there was some text being generated as we're proving it in Python GUI underneath. Is
Yes.
that like a more formal version of the proof?
Okay,
Or
so
what
yes, so what is the text that is generated here? So what is going on as I'm like running the Python graphical user interface? It's running some environment that is using first order logic in the background, and therefore it only like is happy once the problem is fully proven. Right, so here the logic is actually rigid. It's just something implemented in Python, but actually with Anand we were like also implementing something like that in Lean, and we are quite close in connecting. Right? Well, I don't know if connecting the graphical user interface, but basically the logic can be formalized. And but this is not writing the full proof, it's only writing the case splits that it's doing. So it basically represents every object that I can move here with some variable, and it doesn't display the name, which is a bit annoying, right? But then like jumps max is the jump that's over here, and mines is the full list of mines, and so on, right? So basically every object is represented by represented by some variable name, and then it like shows what into which branch in the cases it dives into as I'm solving the problem.
And then the rest is handed off to the automated system.
So the automatic system runs like even before it displays anything. So I make a step in the graphical user interface, let's say induction. Induction has some assumptions, and each of these assumptions, the automation tries to prove it from the text that it knows so far. If it can prove it, it doesn't print anything and it's just happy. If it cannot, it makes this automatic case split and basically prints. Now we're entering a branch where we are assuming this inequality. I don't know if I answered the question.
Yeah, no, that was nice. Thank you.
Are there any questions online? Or out here?
Regarding the slide where you compared the game of Go with mathematics at the beginning,
Yeah.
can you explain your intuition? Like you wrote, the real problem is that we don't know the game. Can you explain a bit more your intuition, why mathematics is more difficult than the game of Go? What is the core reason or
Yeah, like
or reason?
that's what I said, that I think we don't know the game. Well, I think that
That's what does
when a
it
Go player plays Go,
Yes.
he looks at the board, he imagines the move, right? He kind of, and that's almost what AlphaGo is doing, right? Like, yes, it's slightly more like human can do slightly better abstractions than the like tree search, and they and like AlphaGo can search much more options, but like, well, kind of it's close enough. So the what the Go player is doing, and when he's thinking about the position, and what AlphaGo is doing is close enough so that we can say that like that AlphaGo can kind of beat the person just because it can do more research, right? Okay. And the person cannot do too much more clever tricks than the tree search. But in mathematics, you do a lot of other clever tricks than just trying different tactics in. Right, like you can kind of step back. You can, yeah, like you often think about it kind of less formally, right? You play with examples a lot. Or at least like at least in some domains of mathematics, right? But yeah, like I'm looking at combinatorics in particular, right? So I think it's like the combinatorics you play a lot of this example, and
So do you mean that the intuition when solving a mathematical problem is more difficult to learn than the intuition, like for the AI system, or even for the mathematician to learn than the intuition you have when you take it of Go? It's
I
just
think
more
it's more about like understanding what are the steps that the mathematician can do with his pen and paper.
okay.
Right, so that is the point of my,
So then, yeah, yes.
right, so like, I can imagine that you can have in in the formal systems, some more exploration, right? But I think that the formal systems for proving are not very good at exploration, and the reason is because they're not targeting exploration. Right?
It's way to verify.
There are like other systems that mathematicians actually use in their research, like Mathematica and so on, when they can do some exploration. So I think, I think maybe exploration is the right word. But I think the formal systems are missing from having to do that. But like when you do the exploration, the mathematicians kind of understand what the exploration means, right? Then when you just say, well, like you give it Mathematica or
Okay, yes.
Combinatorics is somewhat known for having very inspired steps in proofs at times. Where maybe not so much in sort of computer games and things like that. But in many sort of combinatorics, it's sort of the problems are easy to understand and the solutions are easy to understand, but they're hard because you need some very creative step to sort of come up with the solution.
because there is a crazy trick.
Yeah.
Yes, that's
So
true.
do you think this is making your life a lot harder by focusing on combinatorics?
I think that there are so many problems that you can solve without how Tim would call it rabbit out of the hat. Right? That it is true that like I know an example of such a combinatorics problem that you tell the problem, it's like okay, fine, you have no idea how to prove it, and then you tell the solution and it's magic. And right, like we were posting such problems into like this I know preparations. But yeah, I think that you can solve a lot of problems without like often when you actually want to in the process of making such a proof, which is very magical. There often is a way how you actually find it, and you only want to feel more like a magician when you're presenting it, right? Like you put a lot of effort into figuring out what's going on, and then you like finally find it, and then you can throw basically all of your like research away, and you just like come with this gem and say, hello, look like what I found, right? That's a bit how, but like so of course like the difficulty is that we don't have as good data of how mathematicians are finding these things, but I think it is not something unfindable, right? Yeah.
I guess linking back to the previous points, like the difference between Go and maths is that with Go, like when you make a move for a computer, like it's easy to figure out if it's going in the right direction or if it's a bad move. While for maths, when you do like some sort of logical step, like it's way more difficult to figure out if it's like actually heading towards the proof. So like, I guess
I don't know. I don't think if this is how I would state it, but of course, like in practice, it is hard to figure out, right? But yeah, like the point that I was making was more that mathematicians are aware more. It's more mathematics is more than just research.
yeah. Like research doesn't work. That's like the thing I was saying basically.